Hello, this is Logan Chipkin, and you're listening to the Fallible Animals podcast. Today I speak with Sabine Hossenfelder, an author and theoretical physicist who researches quantum gravity at the Frankfurt Institute for Advanced Studies. She has also written for a number of popular science publications, such as Quanta Magazine, New Scientist, and Scientific American. We discussed her book, Lost in Math, in which she writes about the role of concepts such as beauty and elegance in the research efforts of physicists. We also talk about why research programs into fundamental physics might be running into brick walls, and also the psychological and economic factors that can inhibit scientific progress. Finally, we talk about some fun ideas that Dr. Hossenfelder writes and videos about on her blog called Back Reaction, such as the difference between a grand unified theory and a theory of everything, and also why we're unlikely to ever discover a wormhole. Before the interview, a few announcements. First of all, I recently appeared on Christopher Lovgren's podcast, Do Explain. For those of you who aren't familiar with it, Christopher hosts a critical rationalist and Deutschian podcast in which he has very fun, educational, wide-ranging, and hilarious conversations with interesting people. He and I discussed what I call the big three, those being constructor theory, critical rationalism, and praxeology/Austrian economics, the last of which we're going to explore on this podcast soon enough. Christopher is a great host, and we had a very fun conversation, so please go check that out as soon as you can. Christopher, if you're listening, thanks again for having me. I appreciate it. In other news, I recently had an article come out with Aereo magazine entitled People in the Cosmos, Constructor Theory, in which I weave together history, philosophy, and science. Let me know what you think. I'm always open to feedback, whether it's positive, negative, or anything in between. And finally, if you value what we're doing here on the Fallible Animals podcast, please consider donating to the show. I recently set up a Patreon page at www.patreon.com/fallibleanimals. I'll include a link to that as well on the show notes page, along with a link to Dr. Hossenfelder's blog and website. I very much appreciate your support, and it inspires me to continue to spread these ideas, whether through podcasts or articles. So once again, thank you very much, and without further ado, I give you Sabine Hossenfelder.
Hello.
Hi. First of all, your book, Lost in Math. We live in a time in which I think it can be risky and costly to write content that challenges the ideas of one's own tribe, as it were. So I just want to say I admire that you wrote this book, challenging a lot of the orthodoxies, or at the very least questioning some of the methods that some of the physics community is employing in fundamental physics research. So thank you for writing the book, first of all. It's admirable.
Thanks. So, it was not an easy decision, but I thought someone has to.
Yeah, I imagine you got a lot of probably private pushback that wasn't so pleasant, is my guess, but you don't have to comment on that. So I thought we'd start talking about some of the concepts in the book, because you touch on a lot of philosophy, which I talk about on my podcast, and how it intertwines with physics, and also you talk about the economic and psychological factors that I think a lot of people don't think about when they think about scientists. They tend to think about just robots, but you very clearly write about how that's not the case and the consequences of the fact that that's not the case. But before we get into any of that, in your book, you record and document a lot of your conversations with other physicists in which you talk to them about what they mean when they're employing concepts such as naturalness, simplicity, and beauty. So let's table naturalness, because I want to get to that in a few minutes. But for the listeners, do simplicity and beauty mean the same to the average physicist as they do to the layperson, or are there differences that you think need fleshing out?
No, I don't think that physicists use these words in the same way that the layperson uses them, at least not as it concerns their work. Of course, they may use these words in a sloppy way in everyday life. But when it comes to the theories that they work with, they mean something very concrete. In extreme cases, it's just a mathematical definition that you can write down that, some requirement that a theory has to fulfill. That's what they mean by this. Maybe the example of simplicity is a good starting point, because I think it's fairly easy to understand. So there is a notion of simplicity, which I call relative simplicity, but it's more commonly known as Occam's razor. So this is not what I'm talking about. So this is a good scientific criterion where you basically say, well, if I have two different theories that do the same in sense of explaining observations, then I pick the simpler one. So this is not the criterion of simplicity that I'm referring to. But it's this idea that you want a theory that is simple in an absolute way, in the sense of making as few assumptions as possible. And a good example for this is a quest for unification. In particular, in the areas that I'm writing about, it's a quest for the unification of the fundamental forces. So you may know or not know that presently we have four fundamental forces. So that's gravity, electromagnetism, and then there's the strong and the weak nuclear force. And a lot of effort in theory development in the foundations of physics has been driven by this idea that these different forces should be unified to one fundamental force. And this is ultimately a requirement of beauty. So this is, I think, an example that a lot of people can relate to. It certainly, it would be nice if the universe came from this big, overarching, simple structure, but it may just not be the way that it works.
And you very early in the book open up with an argument that when physicists judge a theory that hasn't been empirically tested yet, they employ these concepts of naturalness, simplicity, and beauty, but you very clearly state that these are in conflict with objectivity. So how is that the case?
Well, there's just no particular reason to think that the world works this way. The reason that physicists use these criteria is that, well, the obvious reason is that they just like working with these theories. And some, I have these interviews in my book, some openly admit it in the sense of saying, well, I have to deal with all this math, and if the math isn't even pretty, then why would I want to do it, basically? So that's one argument. But there's also, and you already hinted at this, there are sociological reasons for why that is the case. It's just something that they have learned. There is also a historical component to this, in the sense that these are criteria that have worked in the past, or at least they believe that they have worked. So certainly when it comes to unification, this is something that has worked in the past. When it comes to naturalness, the situation is far less clear. But so they have this intuition that is based on experience that makes them think it's a good idea to try this again. But then, of course, the question is what makes you believe that it will continue to work? And you have to factor in that they've tried these criteria for 40 years now, and it obviously has not worked, in the sense that the theories that have been devised based on these criteria of beauty have been falsified to the extent that they could be falsified. So that leaves the one that are just unfalsifiable, that I think scientists should not be dealing with to begin with. But so it's definitely a very subjective criterion, based partly on personal experience, on the group that people are part of, and also just on what they like and dislike.
Do you ever think that we'll have a physical theory of these ideas, such as beauty, simplicity, and well, we'll get to naturalness in a second, but do you ever think we'll have a physical theory of these ideas such that it'll no longer be according to one's subjective preferences?
I'm not even sure what you mean by that. You can have a physical theory that fulfills these criteria. So you may be asking, will we ever find a theory that is beautiful in exactly the way that people now mean it? But will we have a theory of how these concepts of beauty come about? I kind of doubt it, because that would basically mean, understanding human cognition in its entirety. So I don't think that this would be the case.
In that case, I would love to hear your thoughts on, so you write in your book that Gian Francesco Guidice, I hope I'm pronouncing that person's name right, he came up with a theory of how we might measure naturalness. Do you think that his theory will stand the test of time? And also, how do our current best fundamental conjecture theories stack up against this naturalness measurement?
Well, so it's not so much that he has a theory in the sense that he explains some observation with it. What he has put forward is a mathematical way to measure this particular type of beauty, which is called naturalness. And I can explain what this means, but let's just leave this standing for now. So what can you do with that? Well, you take any theory that you have newly developed and then you use geodesics measure, and you can find out how beautiful this theory is, basically. So you get a number, it says, well, it's very beautiful or it's not so beautiful. So that's what you do with it. And it was widely believed until, a few years ago that this is a good way to find out which theories are promising and which are not. So the more beautiful theories were considered to be more promising. But this is science, so we're getting data about what nature does and doesn't do. So the Large Hadron Collider has delivered a lot of data, and it has not found any of these supposedly so promising, naturally beautiful theories. So they've all been ruled out. In particular, these ideas of supersymmetry and stuff like that. None of this actually showed up, despite the fact that many theoretical physicists were pretty confident that this would be the case. So what have we learned from this data? Well, we have just learned that this argument from naturalness is wrong.
And so could we please define naturalness quickly for the listeners?
Yeah, so naturalness is basically says you that if you have a theory that is formulated in mathematical equations, which is the case for all the theories in physics, then the numbers, the pure numbers that appear in these theories have to be close to 1. So they shouldn't be very large and they shouldn't be very small. So that's the general idea. And then particle physicists use a slightly more sophisticated notion of naturalness that's also known as technical naturalness, that says sometimes small numbers are allowed if you have an explanation for why they are small. And so any theory that does not fulfill this criterion, say you have a small number but you have no explanation for it, is considered to be unnatural and ugly.
Very interesting. Very interesting that didn't pan out. So, yeah, we'll see. Maybe new criteria.
Does it surprise you? Would you have thought that an idea like this does pan out?
Well, no, but I think I would come at it at a different way than you have. The reason why I wouldn't be surprised that such an idea didn't pan out is because I'm not certain that theories have to necessarily take the form that they must be mathematical in a particular way, or that maybe here we do agree that numbers have to be close to 1. So you also write about the philosopher Richard David's definition of elegance, which is another one of these ideas. And he defines elegance as unexpected explanatory closure, which is something I had never heard of before. So please correct me if I'm wrong, but this is essentially both the unanticipated connection between entities that were previously considered unrelated, and also it's the birth of new, previously unknown entities, both abstract and physical, in accordance with the theory. You imply that you're not such a fan of this, or at least that this definition of elegance doesn't really solve any problems. So why are you not a fan, if that's the case? And is it true that it doesn't really solve any problems in our worldview?
Well, the problem with this idea of elegance or unexpected explanatory closure, whatever way you want to put it, is that it's just not an objective criterion. It basically tells you that a theory is better if it surprises you. But, some people may be surprised by one thing and other people will be surprised by some other thing. And in any case, what you are surprised by depends on your knowledge. A lot of people are probably still surprised by general relativity. But if you've spent 15 years of your career, pretty much as I have, thinking about general relativity, then maybe it's not so surprising anymore. So what kind of criterion is this? Well, maybe it's a criterion by which you may want to decide if you want to continue working on it, because, on a personal level, I can understand that this is relevant. But it's not a criterion that you should draw on to judge the promise of a theory.
Right, yeah, I agree. Although it could be that there's some objective way of explaining the notion of surprise, but who knows?
Maybe there is, if someone came up with this, and so let's just consider that this is possible. Someone would come up with a scientific theory of surprise that you could apply to theories of physics. So you could figure out how surprising is this theory in a quantifiable way, maybe. Well, then you could go and test if this has historically worked. Have surprising theories indeed been more successful? And if you find out that, yes, this has been the case, I would say, well, then that's a very good reason to continue using this criterion. So I would totally accept that, but it's not the situation that we're in.
Right, so you really more or less want any of these theories, whether it's a theory of elegance or a theory of naturalness, you really want them to be tested and tested successfully in order to be taken seriously.
Yeah, well, I'm a scientist after all, so, I suggest that we use the scientific method. And when it comes in particular to these ideas of simplicity in the way that I just talked about, with this idea that unification must be continued, or arguments from naturalness, then we have 40 years of evidence that they are not working. And this is just evidence that I think we should be taking into account. So these are basically metaphysical criteria that physicists are drawing on, but they are criteria that demonstrably have not worked for a long time. And I think that physicists should take this into account if they continue developing new theories.
So this leads us, because then the follow-up natural question is, well, why haven't they necessarily taken them into account? And then you also write about in your book, I think it's more or less the second half of the book, or towards the end of the book, you write about the perverse incentive structures in academia that might be inhibiting progress, and also the economic factors. So for example, you explained that since funding is scarce, scientists working on theories that are unpopular to begin with, and that require more time to develop than other rival theories, are unlikely to receive funding. I had never even considered that sort of economic notion. It's very interesting to me. And then you spend a lot of pages detailing consequences of the fact that science is a social enterprise, which is something I think about a lot. So what are other social and maybe psychological reasons why scientists can sometimes get stuck on unchecked hypotheses and outdated ideas, to borrow your phrasing?
One example is that, and I have to admit I know this from myself, that it can be just psychologically very hard to give up on an idea that you have invested a lot of time in, even if it becomes increasingly obvious that it's not working. So I think that there's a strong psychological driver to just continue this and try to make it work. And now there is this social aspect to the problem in the scientific community, at least in the ones that I'm familiar with, where this psychological bias, that falls in the category of loss aversion, is supported by it being very difficult to actually start working on an entirely new topic. The problem is that if you want to get a new position, you want to get your contract renewed, or you want to get a new grant, to hire people or just to pay yourself, you have to demonstrate that you have experience in this particular research area. So you're basically forced to continue doing what you've been doing for a long time already. If you were to say, well, okay, look, I've tried this, it doesn't work. Now I'll go and do something entirely different. No one is going to give you money, and no one is going to give you a job. So you would think that for science to work properly, we should be taking into account these psychological biases that people already bring and organize the system so that it works against them. But instead, the exact opposite is the case. The current organization of the system actually supports these biases. And you already mentioned another example, which is that people like to work on what is popular. So this is a very human thing to do. We like company, basically. We like other people to like us. So it's entirely understandable. But it's also a bias that we bring to judging theories. It's not objective. If you look at the theory and ask yourself, well, how many other people also like it? That's a social question. It's not a scientific question. And now the way that we presently organize scientific communities is that you are getting rewarded if you work on something that is popular with other people, because it makes it much more likely that your work is getting cited. It makes it much more likely that someone is going to create a new job and pour money into this, and it's more likely that you will get hired. So again, the current way that we arrange interactions in the scientific community actually makes the problem worse instead of acting against it.
It's interesting to hear you lay out all of these problems, and it's funny because my natural inclination is to just be positive and optimistic in general in life, not so much that it becomes a naivete, but just in general, it's nice to look at all the progress science has made, but on the other hand, we have to be honest actors and we have to be adults about it and say, look, here are the problems with the current structure, and if we really want to make further progress, we have to deal with them. So I really appreciated that part of your book, because I think it's not really talked about that much.
Well, so the knowledge is there. So this is something that sociologists of science talk a lot about, and also people who work on bibliometric analysis. There's a whole area of research called scientometrics. That's basically about how to measure scientific progress. And so people in these areas are very worried about how certain ways of measuring scientific productivity has a strong influence on the way that researchers choose what to work on. So this knowledge is definitely there, but the problem is it's not with the researchers who are actually active in these disciplines. So the knowledge is not where it needs to be.
That's right. Yeah, I think I read a few of your blog posts where you talk about that the knowledge is there, but it's not distributed in the ideal way.
Yeah, right. So I actually think that stuff like this should be part of every scientist's education. It's so important to understand how your research environment works, all these social pressures that you have to be aware of, because otherwise you're not able to make objective judgments. And that's really, really important if you want to be a good scientist.
Right. Scientists are not brains in a vat flying through space.
Yeah, and you have to be aware of this. So then you can at least try to do something about it. And that's just presently not the case.
Yes, totally agreed. So before we switch to talking about some of the fun ideas on your blog, because I think you write about a lot of these ideas that are sort of roughly in the collective consciousness, but you seem to straighten out a lot of confusion that it seems like maybe you lay at the feet of journalists, but I don't want to put words in your mouth necessarily. But before we get into your blog, I wanted to push back a little bit on one thing you wrote in your book. You wrote that when science progresses, when our knowledge expands, the room for philosophy inevitably shrinks. Now, I don't think that's the case, because with every scientific advancement, new philosophical vistas and questions open themselves up to us that we wouldn't have considered previously. Do you disagree with that?
I think that's right. You can take the point of view that if the available range for philosophy is infinitely large, then it does not get smaller. What I meant to say with that is that as science progresses, it is able to answer certain questions that were previously in the realm of philosophy. And that has happened in the past, and it will certainly continue to happen. And I think that's just the normal way that you expect things to go. Maybe there are also some questions that will forever remain philosophy.
Yes, I agree with that. And I think also the two are intertwined. I think sometimes science informs philosophical problems, and also philosophy can inform scientific problems. For example, the whole field of philosophical epistemology, the theory of knowledge and how it grows, directly impacts how we should be doing science.
Yes, though I think, at least from what I've seen of the interaction between scientists and philosophers, it's more often the case that science influences what the philosophers think about than philosophy influences what the scientists think about. And at least in the foundations of physics, I think that's not a good thing.
You think it's not a good thing in the sense that you think it would be better if philosophers impacted or influenced the way fundamental physicists did their work, or what did you mean by that?
Yes, well, not necessarily in the sense that the philosophers, that I'm expecting philosophers to do something specific, but in the sense that I wish physicists in those areas would take philosophers more seriously. Like, if you look at the examples that I was just talking about, like these issues with naturalness and metaphysical arguments and so on, is it allowable? Is it possible for scientists to use these kind of criteria? I mean, these are questions that philosophers have been thinking about. And I think if physicists had been aware of what they are doing, they would have been able to have a constructive conversation with philosophers. But this never happened. And it's still not really happening. There are some events, and I've been to a few of those, where this conversation is slowly beginning to happen, but it's nowhere near the level where I think it needs to be.
Maybe it's slowly more and more beginning to happen because at some point the rubber does have to meet the road in the sense of, and as you've said a few times now, you have 40 years of stagnation, arguably, in certain areas in fundamental physics. Maybe it is time to go back to the drawing board, as it were, and question some philosophical foundations in one's worldview.
Yes, that's certainly true. It's just that if you talk to people in these areas that I'm writing about, particle physics, astrophysics, cosmology, also some areas of quantum foundations, they would very, very strongly disagree that we have a phase of stagnation because they think everything is great. They're making huge progress every single day, basically. It's sometimes I think it's actually totally ridiculous what they're talking about. Like if you talk to people in quantum gravity, so that's maybe an example. Quantum gravity, that's this question like what's the quantized version of Einstein's theory of general relativity, in a sloppy way, that's the question. And this is something that people have been asking since the 1930s. So it's an 80-year-old problem. We still don't have an answer. We're not even getting closer to answering it. But you ask anyone working on quantum gravity, they're like, oh, we've understood so much. It's just that it never seems to result in anything. So, but yeah, I mean, I think that you get this illusion of progress just because people write a lot of papers and they talk about a lot of things. And, every once in a while, they answer a mathematical question, basically, and that counts as progress. But there's no output, basically. As you said, how did you put this? The rubber has to meet the road, and that's just it's not happening.
Right, exactly. And yet, the illusion is kind of there because there are so many publications, I think, is part of it. But publications does not equal problem solving.
Yeah. And conferences, of course. Conferences are also, yeah.
All right, so piggybacking off that, we'll switch to your blog, Back Reaction, which I'll link to in the show notes page for sure. Let's just make one more remark about the sort of incentive structure around academia. So on your blog, I read one of your posts, and you write that physicists still operate by the, quote, just look idea from the 19th century. They do not think about which hypotheses are promising because their education has not taught them to do so. Such self-reflection would require knowledge of the philosophy and sociology of science, and those are subjects that physicists merely make dismissive jokes about. And you also say, by the way, that this lack of philosophical knowledge is bleeding into other areas such as ecology and medicine. So let's pretend that I'm one of these scientists and I hear you say all this, or I read your post. So, okay, what would you have me do then?
Well, so I think that, I'm not really qualified to say a lot about areas that I'm not familiar with. So maybe let me focus on the stuff that I know most about. So what I'm referring there to with this just look argument is that we have this question, what experiment should we invest in to make progress? I think what's the natural thing to happen in any discipline of science at some point is that it becomes increasingly more difficult to make new experiments that test something we have not tried already. And if it becomes more difficult, it also becomes more expensive. So it becomes this economical burden on society. And it also brings up the question that you have to be really, really careful in selecting the right experiment, because there are only so many experiments you can do. And if you pick the wrong ones, you're not going to get any information that will help you to develop new theories. And so I think that in the foundations of physics, we have been very, very careless in selecting the experiments that we have done in the past, 20, 30 years or something. And you see this in the media, every couple of months, there will be a new report saying, well, there has been this experiment and it didn't find anything. Experiments that search for these weakly interacting massive particles or for axions, like I just came across some articles about this a few days ago, because there was another experiment that delivered a null result. And also the searches for new particles at the Large Hadron Collider, and searches for fifth forces and all that kind of stuff. They all came back empty-handed. And I think we just have to be more careful where to invest our money. And as you just quoted, I think that this requires that people in this community undergo some self-reflection of how they make decisions for their experiments and what these decisions are informed by. It's no longer sufficient that everyone just screams, and whoever screams the loudest gets the money, and it doesn't really matter because progress will happen somehow anyway. So I think that there are too many people in these disciplines that still operate under this assumption that progress is kind of inevitable. And what I was trying to get across in this blog post is that in this, when it comes to this problem, the foundations of physics are kind of the canary in the coal mine, because we're the first to see this problem, because it's a very old discipline. If you compare it to fields like ecology or medicine or something like this, these areas just have a lot to explore. That is not terribly costly. But sooner or later, all these disciplines will run into exactly the same problem, that experiments will become more and more difficult to finance, collaborations will become larger and larger. And then they will have to ask the same question, like, how do we smartly make decisions in these large communities? And that's difficult, because every time you have a large group of people who think very alike, you run the risk that you run into what's known as social reinforcement, or that's more colloquially known as groupthink, where people just tell each other over and over again that they're doing the right thing, even though for an outsider it may be patently obvious that that's just completely crazy. So one has to think about how to make smart decisions in these large communities, and no one's really thinking about it.
Well, no one except you, maybe.
Well, yeah, so let me correct this. No one in these communities is seriously thinking about it. There are certainly a lot of people working on decision science who are addressing exactly this question, but that brings me back to what I said earlier. The knowledge is not where it needs to be.
Right, exactly. I actually I saw that tweet that you were challenging one of these articles. Anyway, so okay, switching from talking about problems in fundamental physics, I wanted to talk a little bit about some of the ideas that I came across on your blog post, because you put out these very concise videos, and then you also, I think you transcribed directly the script from the videos into a transcript, which is very nice. So if people want to read your ideas, or if they want to watch you provide both options on your blog. So one of the clarifications you make in one of the videos I saw was the difference between the grand unified theory and the theory of everything. So I was wondering if you could please tell me and my listeners, educate us about what is the difference between them and why does it matter?
Yes, great question, because I should have clarified this earlier when I was talking about this unification. So as I said, we have these 4 different fundamental forces gravity, electromagnetism, and the two nuclear forces. And a grand unification is if you combine electromagnetism with the two nuclear forces. Why only those three, you may ask? Well, because those three have quantum properties. So they are about particles that obey Heisenberg's uncertainty principle. So if you manage to combine those three to one single force, that's called a grand unified theory. The theory of everything should also include gravity. And now the issue with gravity is that this theory does not have quantum properties. So there's no easy way to just combine it with the other three forces. So this requires that you quantize gravity and create a theory that is known as quantum gravity. So this theory of everything that a lot of people are looking for combines both this to-be-found theory of quantum gravity and a grand unified theory.
Gotcha. Thank you very much for that clarification. So which do you think we will discover first? Or do we have to discover one before the other?
No, not necessarily. I mean, if you ask string theorists, then we have already discovered the theory of everything, and the theory of everything is string theory, and all the rest are details that they will work out, But the thing is that we have no particular reason to think that either a theory of everything or a grand unified theory even exists. It would be nice, if nature was simple in this particular way, but it's not necessary for anything. It's different when it comes to this theory of quantum gravity, because the theories that we have right now, these four forces, are the way that it stands at the moment just mathematically inconsistent. They don't work properly together. And that's a problem which does require a solution. So for this reason, I do think that we're most likely to first find a theory of quantum gravity, and then, we will see if there will ever be a grand unified theory or a theory of everything.
So another concept that was completely new to me, but that in hindsight probably caused so much confusion for any of the times I read into physics. And this is a little bit more technical and not as, I think, popular in the collective consciousness as the previous idea we had talked about. But it's the difference between time reversal invariance and time reversibility, and that these are not the same. I don't think I ever knew that these were not the same until I read your blog post, so thank you for that. So could you please maybe give us an example of the difference between them, and why is this difference significant in the grand scheme of physics?
Oh my God, example. I'll have to see if I can think of something. But so time reversal invariance, well, maybe let me start with the other one. So time reversibility just means that you can run a certain physical process backwards, like basically the same way that you can run a movie backwards. Usually the way that some theory in physics works, that I tell you the state of a system at some initial time. So this is called an initial condition. Say I give you all the momenta and positions of particles or something, and then I give you an equation, which is also called the evolution equation. And with this equation, you can calculate the position and momenta of all the particles at any other time. But you could as well take some state in the future and run this equation backwards. So these two things are entirely equivalent. It's just that for practical purposes, normally you wouldn't run it backwards. But in principle, you could do it. So this is a time reversible process. In principle, there are evolution laws which do not have this property. Now, if you have some process that is time reversal invariant, then it means that it looks the same if you go into the future as it looks if you go into the past. There are fairly simple examples that you can think of, like if you have, say you have, someone sitting on a swing, okay, and it goes back and forth. and let's forget about friction for the moment, you could run this movie forward and backward and it would look the same. So, unless you look at the details, right? But you get roughly what I'm aiming at. So you couldn't tell which the direction of time goes. So this would be an example of a case that is invariant under this time reversal.
So do you think the theory of everything, as we've been talking about it in that sense, will that be time reversible and will it be time invariant, or will it only be one of the two? Or neither? Or is it far too early to tell? And what a silly question of me to ask.
So, well, of course, we don't know, right? That's the obvious thing to say. Personally, I think that this theory will probably be time reversible. It's just that this assumption has worked very well for the theories that we already have, and there's no particular reason to think it should break down. This notion of time reversal invariance is not a property of the theory itself. It's a property of solutions to the theory. So it's not something that you can ask of your equations. And we know just from observations that the universe is not time reversal invariant. It was different in the past than it is going to be in the future if we extrapolate our equations. So I should make an asterisk here and add a footnote, because there are people saying basically that the universe could go through cycles that all pretty much look alike. And that's very similar to this example of the oscillator that I was talking about. But it's hard to make this compatible with the brute fact that we do observe our universe has an error of time, in the sense that we all only get older and never younger. So this makes it very hard to make any such ideas compatible with time reversal invariance.
I guess time will tell. No pun intended.
Yeah.
So I want to end on a sort of fun, quirky idea, also in the cosmic realm of science. I read one of your blog posts about wormholes, and I always thought of wormholes as sort of this fun, science fiction-y type idea, but I think if someone were to ask me, and I'm just a layperson really, are wormholes physically possible, I think I would have said yes. But you write that mathematically wormholes are solutions to the equations of Einstein's general relativity, but that there are actually all sorts of equations to general relativity's equations that don't in fact correspond to physical reality. So basically, wormholes are mathematically possible, but they're not physically possible. Do I have that correct?
Yes, well, more precisely, I should say they are, for all we currently know, they are not physically possible. So there are, as you say correctly, there are certain types of wormholes that are solutions to Einstein's theory of general relativity, but there is no physical process that you can actually use to make them. Roughly speaking, the problem is that in these solutions, the wormholes must have existed since forever. So strictly speaking, they are never formed. They just have to somehow be there already at the beginning of the universe. So it's different with black holes. Maybe this comparison is helpful, because for black holes, we know processes, physically possible processes through which they form. You have a supernova that undergoes a core collapse or something like that. So this will create a black hole. But there's no process that we know of that would be able to create a wormhole. And there are other ways to maybe create wormholes, but these all require that you have certain types of matter that has negative energy density. And these types of matter just do not exist for all we currently know. As I write in this blog post, it's something that you can write down mathematically, and you can work with it on a sheet of paper, and I'm sure it's a lot of fun, but there's no reason to think that this has some correspondence in reality.
So could there be as yet undiscovered principles in physics that themselves constrain which solutions of general relativity's equations are physically possible and which are impossible?
That's a very good question. Yeah, probably. This could be the case. Yeah, so I don't see any reason why this should not be possible. Yeah.
Because that would be very cool. Because we basically general relativity, what you would have all of these different solutions that some of which correspond to reality, some of which don't. But then maybe there's another theory that itself explains why only some of those general relativity solutions are permitted in our universe or our reality.
Yes, well, we kind of already use some of such criteria that may be similar to what you are talking about, which are certain types of energy conservation, basically. So this is something that basically puts constraints. We are also using certain types of basically boundary conditions at infinity that also restrict the type of plausible solutions. But there could certainly be other criteria that we have yet to discover that could help us to decide which solutions are and are not viable.
That would be yet another very exciting avenue which physics may go down, and I look forward to hearing and reading all about it. All right, well, Sabine, thank you very much for coming on the podcast. I appreciate your time. I understand you're very busy. As I said at the beginning, you're doing very important work, and you have my support, and my listeners and I very much appreciate all of the information that you've been giving us, and I hope they read your book. Are there any final thoughts that you want to share with me and my listeners before I let you go?
No, it was fun talking to you. Thanks for having me.
All right, thank you very much.
Bye.
See ya.